Hello, in this video we will apply everything we've learned about rational functions to find the equation of a rational function given its graph. So we're going to determine a formula for a rational function r that has the graph below, and it's known that the limit of r of x as x increases or decreases without bound equals 6. So keep in mind that's actually telling us the long-range behavior of the polynomial. So it's telling us that there is a horizontal asymptote at y equals 6. The limit of r of x as x approaches -3 from the left is positive infinity. So it's just confirming here that we have a vertical asymptote at -3. And then the limit of r of x as x approaches -3 from the right, that's also confirming this vertical asymptote at x equals -3. So we know that in rational functions, the factors of the numerator give us the x-intercepts. So we have an x-intercept at 2, which means there's going to be a factor of x minus 2. We also see the graph is bouncing off of that x-intercept. So from our previous knowledge with polynomials, we know that the multiplicity of that 0 must be even. So I'm going to take x minus 2 and square it for now. Maybe it's x to the 4th, x to the 6th. We'll go back and analyze that momentarily. We know that the vertical asymptotes are a result of the denominator equaling 0. So we know there's going to be a factor of x plus 3 because of the vertical asymptote at x equals -3. And then there's also a factor of x minus 4 because of the vertical asymptote at x equals 4. And then we also notice there's a hole when x equals 8, and that happens as a result of having a common factor in the numerator and denominator. So we know both have the factor x minus 8. And so I mentioned earlier we would check the multiplicity of x minus 2 squared. And we're going to do that by thinking about the long-term behavior of this polynomial. So because there is a horizontal asymptote at 6, in other words, this limit of r of x as x increases or decreases without bound is approaching a specific value, that allows us to conclude that the numerator and the denominator must have the same degree. And so the numerator, if we were to add up these multiplicities, has a degree of 3, and the denominator also has a degree of 3. And that's good. We want them to have the same degree in order for this long-range behavior to be true. Other things we can think about, the graph changes sign on either side of the vertical asymptote at x equals -3. So the factor x plus 3 would need to have an odd multiplicity. And the same thing is happening at the vertical asymptote of x equals 4. The graph changes sign, so the multiplicity for this factor x minus 4 should be odd. Now there's two ways that we could finish up this problem. We do know that there could be some type of vertical stretch or compression. Because the horizontal asymptote is y equals 6, we actually could just conclude that this is going to be r of x equals 6 times x minus 2 squared, x minus 8, over x plus 3, x minus 4, over x minus 8. That way the ratio of the leading coefficients would just be 6, satisfying our rules for horizontal asymptotes. Alternatively, if you didn't remember that for sure, or you just wanted to check your work another way, then what we could do is use this other point. There's a y-intercept at -2, so we know that the output is -2 when the input is 0, and we could solve this equation for A, and when you do that, you would find out that A equals 6. So that would confirm that our rational function of this graph has an equation of 6 times x minus 2 squared times x minus 8 divided by x plus 3 times x minus 4 times x minus 8.